All right. Our next speaker will be Professor Paul Davies. Paul is a cosmologist, an astrobiologist. He is someone who has dedicated his life to looking at fundamental questions. You know, why do the laws of the universe are what they are? Why are they amenable to life and to consciousness? Why does the universe exist? Okay, and what is life? He has a number of books examining these extremely interesting questions. I particularly like his one called The Goldilocks Enigma, which is devoted to this question of why the universe is compatible with life. I think it's an extremely interesting question. In any case, he's going to talk to us today about what is life. So, Paul.
Thank you, Bob, and thank you to the Mars Society for inviting me to speak. Again, I've been to a number of the meetings. This is the first one that I've done via Zoom, but I think we're all getting used to the Zoom world. And as Bob mentioned in the opening remarks, my interest is really in foundational questions. What is life? How did it begin? And how widespread in the universe might it be? Okay. Right. Well, let me start then at the beginning. So the question of whether or not we're alone in the universe is one of the oldest problems, oldest and deepest problems in the history of human thought. And for most of history, it's fallen almost exclusively in the provinces of religion and philosophy. But in the last few centuries, science has been able to make a contribution as well. And at the birth of science as we know it, belief that there is life beyond Earth was pretty widespread. So here is a quotation from Kepler, who uses a very curious philosophical argument that our planet has a moon and Jupiter has 4 moons. So what are they for? Well, presumably to make life agreeable for the inhabitants of Jupiter. So he was deducing on those grounds that Jupiter has life. And there were arguments for and against on both philosophical and theological grounds. And this rumbled on right up into the 19th century. But a more scientific view then began to prevail. Nevertheless, belief that Mars at least might be inhabited was fairly widespread. And as I'm sure everybody listening to me knows, Percival Lowell built this observatory at Flagstaff in Arizona, specifically to map the canals of Mars. This is one of his maps. These straight lines, which turned out to be purely imaginary, were what some people supposed were dug by thirsty Martians to irrigate their planet. And no doubt this sort of Mars fever played into the success of H.G. Wells' novel War of the Worlds. But a more sober assessment already at that time had kicked in. And it's a curious fact that the theory of evolution, which we associate mainly with Charles Darwin, was independently deduced by Alfred Wallace. And in a 1904 book, Wallace turned his attention to what he called man's place in the universe. And I think we can just read that to mean that the possibility of intelligent life in the universe, and draws the conclusion that the improbabilities of the independent development of man, read intelligent life, even in one other world, are now shown to be so great as to approach very closely the actually impossible. So he was putting a firm dampener on this speculation about life on Mars, or indeed anywhere else beyond Earth. And Carol was saying that there are not many people probably attending today who remember Viking and the young Carl Sagan and so on. Well, I certainly do. So I'm one of the old guys, and I was interested in the search for life beyond Earth as a student in the 1960s in London. And the prevailing view at that time was very much that of Wallace. So, for example, Francis Crick, co-discoverer of the structure of DNA, said that life seems almost a miracle. So many of the conditions for it to get going. And in those days, I was really interested in life beyond Earth, but one might as well have professed an interest in looking for fairies, hence the picture on the screen here, because it was considered self-evidently absurd that something as complex and specific as life would ever arise twice in the universe. This was echoed by Jacques Monod, another Nobel Prize-winning biologist, and again, somewhat sexistly, man at last knows that he is alone in the unfeeling immensity of the universe, out of which he emerged only by chance. So here we're talking about like round about 1970, overwhelmingly, the thought is that life on Earth is a bizarre fluke, probably unique in the entire universe. But fast forward just about 20, 25 years, just a generation, and a very different view began to be expressed specifically by Christian de Duve, yet another Nobel Prize-winning biologist, who said that life is almost bound to arise wherever physical conditions are similar to those on Earth. And he coined this ringing phrase, life is a cosmic imperative. The curious thing that I find is that this shift in sentiment from the 70s to the 90s is almost entirely sociological and philosophical. That is, the facts hardly change at all, the scientific facts. This really predated the discovery of exosolar planets, although I think everybody assumed they were out there. But in particular, our understanding of how life originates really hadn't advanced very much at all in these 20 years. So we've gone from life being a bizarre freak to being a cosmic imperative. And of course, there are various positions in the middle. But an argument that's often used, still is used by many people, is that the universe is so big, there must be life out there somewhere. So if not on Mars, sooner or later, you would find an Earth-like planet with life on it. And then the question is, what is the justification for that statement? Must is a very strong term. What are the odds? Well, we can do the arithmetic. There are probably about 10 to the 22 planets within a Hubble volume. That's the volume of space that we can, in principle, access. And so we can have a go at trying to estimate what is the probability of life somewhere out there. And Mary Wojtek has expressed, I think, this sentiment that the universe being so big has to have. Sorry, I'm manipulating my screen here in a very complicated way. Anyway, no. Bear with me, I'm sorry. I was trying to read Mary's quotation, which is obscured by one of the boxes on the screen, and I've lost my mouse functionality because of having to plug in the external microphone. Anyway, so she's expressing the point of view that it's impossible to imagine that there wouldn't be life out there somewhere. So these are very strong statements. Now, what is clear is, of course, there's plenty of real estate on which life as we know it at least, might arise. Many estimates of the number of Earth-like planets, depends a bit on how you define Earth-like, within the solar system. And so, typically we're talking billions. But of course, it's not enough to have a planet like Earth for there to be life. In order to have life on an Earth-like planet, life has to arise on it. So habitable is not the same as inhabited. Somehow non-life has to turn into life. And so however many candidate planets you have, everything hinges on the probability of non-life turning into life. And the question is, in the case of life on Earth, was it a bizarre fluke? That is a dream run of chemical reactions of extraordinary improbability? Or is there some sort of life principle in the universe that fast tracks matter to life wherever conditions are suitable? If there is a life principle or a cosmic imperative, as Christian de Duve put it, we have yet to discover it. It's an act of faith that there might be such a life principle. I'm agnostic about it. I think there might be, but it's certainly not anything that comes out of the laws of physics and chemistry. It's something that we have to add on or discover in addition to those things. What did Darwin have to say on the matter? Well, wonderful quote, "It's mere rubbish at present thinking that one, thinking of the origin of life, one might as well think of the origin of matter." Sort of curious thing that physicists now can explain the origin of matter, but cannot yet explain the origin of life. And the problem here is a very simple one, but it's often overlooked. It's if you don't know what the process was that turned non-life into life, and we don't know, we just assume it's a sequence of chemical reactions, don't know what they were. If we don't know that, you can't estimate the probability that it's going to happen, because you can't estimate the probability of an unknown process. So it's simply impossible to conclude on the basis of a very large number of potential sites for life that life will be widespread. That will only be the case if the transition from non-life to life is favored. And we simply don't know that it is in our present state of ignorance. Now, of course, there's plenty of work, prebiotic synthesis experiments, such as the famous Miller-Urey experiment. The problem here, there are really two problems. One is you don't get very far down the pathway to life. This experiment succeeded in making some amino acids, but they're easy to make and you find them in meteorites and all over the place. So it's no big deal really that you can make amino acids. The implication at the time was if Miller kept going for 1 million years or so, that maybe something would crawl out of the apparatus. But I think to be realistic, these are just baby steps along a very, very long road to a truly complex living thing. So that's part of the problem, the complexity barrier. But there's a more fundamental problem in my view, and I'd just like to mention it very briefly. If you go to a physics department at a university and say, well, what is life? As Schrödinger famously asked, you'll be given a narrative in terms of matter and force and energy and entropy and molecular shapes and binding affinities and so on. All that's really rather well understood. Those people are very clever. But if you go to a biology department and ask what is life, you're given a completely different account in terms of things like instructions and transcription and translation and signals and coding and encryption. And this is brought home most forcefully with the recent technology of CRISPR, which enables us to rewrite the book of life, edit the genes. So genes are like a transcript, set of instructions, which we can get in and rewrite. And so the upshot is that biologists use the language of information, physicists use the language of stuff, of matter. So we've got stuff versus bits, basically. And the informational story pervades biology. It's not just the translation of the instructions from DNA to proteins, the so-called book of life, but genes form regulatory networks, sometimes of great complexity, turn each other on and off. Information swirls around them like modules in an electronic system. When we think of a developing embryo, then it's a striking example of how patterns of information coupled to patterns of chemistry to exercise exquisite control. So it's not just a matter of a head count of informational bits. The quality of the information is something very profound, very mysterious. And of course, the big information processor par excellence is between our ears in the human brain. And this extends right up to planetary scales. I say that the biosphere is the original World Wide Web. It really is a web of information. So we can only understand the origin of life by understanding its information. And no example better illustrates the conceptual gulf that exists than the universal genetic code, because this tells us that the instruction set for life is encrypted in a code which is pretty much universal across all known life. It's encrypted information. For these instructions to be acted upon, they have to be decrypted. So there is complex machinery that turns this software into hardware output. And the origin of this is still deeply mysterious. How did molecules write code? How does hardware produce software? Nobody knows. So that's a huge gulf in understanding. And we don't know whether the emergence of software control is something which is written into the laws of the universe in some way, that there's a life principle that ensures that a mishmash of chemicals proceeds down that path with emergent software. It's easy to use the words. It's really very hard to think of what this principle might be or how it might operate. So we're completely in the dark as to how this is done. So contrast this, for example, you want to go to Mars, does it have a magnetic field? Well, how do you test that? Well, you build a magnetometer and it'll read out, as it flies over Mars, read out what the local magnetic field might be. Not very much in the case of Mars. But we don't have such a thing for life. We don't have a life meter. Wouldn't it be nice if we could fly something like this to Mars or Enceladus or wherever is your favorite place? And if it detects life, it would simply read it out. And it would also read out the steps on the way to life. So it may go to Titan, for example, and say, well, it's got 83.4% of the way to life, but it didn't really make it after 4.5 billion years. Somehow that seems ridiculous. Somehow we are missing a fundamental concept if we think that we can just sort of measure the degree of lifeness in a chemical mixture. But we really want to do that. We really want to distinguish also between a prebiotic soup that might be complex enough to be approaching the formation of life from the detritus that comes from once living things that have got mashed up, for example, in plumes coming out of Enceladus. We don't know how to distinguish those things, and maybe they can't be distinguished. So these are really fundamental conceptual issues. But let me be stark about it. Suppose we go to Mars and we find an amino acid. Would we be excited? Would we say there is life on Mars? I don't think so. As I've indicated, amino acids are really very easy to make. But suppose we found a ribosome, or more to the point, many ribosomes, then I think everybody would sit up and take notice. So what is it in the spectrum between an amino acid and a ribosome? At what point would we say, aha, this is fishy, there's something going on here, it must be life? Well, the big problem is we lack a definition of life. And there's a famous parable from the geologist and theologian William Paley, who in the end of the 18th century described walking across a heath and coming across a watch lying on the ground, and you pick it up and you examine it and you see how all the components interlock in a felicitous manner, and you assume it must have been designed for a purpose. And Richard Dawkins, in his book, The Blind Watchmaker, which uses that parable, says that life is precisely that which mimics the appearance of design. So one possible definition of life is it has design-like qualities. And let me give a striking example. If you saw this, I think you'd be pretty convinced that life was responsible. We would not expect that type of shape on the moon or elsewhere to arise from non-living means. But how do we capture this in a mathematical theory? How do we build a life meter? How do we come up with some sort of measure of lifelikeness? Well, I think it's a very deep problem, but my colleague at Arizona State University, Sarah Walker, in collaboration with Leroy Cronin at the University of Glasgow, has come up with a proposal, a very clever idea. So they insist that life is really a process. It's not a thing. It can't be disconnected from the molecular pathways that lead to it. So it's pathways, not structures, that they think are important. And in a recent paper, they show how these pathways could be analyzed with suitable chemical apparatus and a mathematical function assigned to the improbability of those pathways arising by non-living means. And so it's a sort of, in some ways, it's a circular definition of life, because you can take molecules produced by life and then you can measure their pathway complexity. They define something called the assembly number, the A number. So this is assembly theory. and they assign a value of 15 to the transition between non-life and life. So they're convinced that it's possible to actually fly a mission, to sample the organic material and assign an assembly number to it. And this is a definition that does take into account the software aspects, in the sense that the pathways represent the canalization of information and the processing of information. So it's an informational-based definition, somewhat related to the quantity called logical depth that's been discussed for a number of years. Don't have time to dwell on it. I just want to bring this to a fairly sharp conclusion. I lost a minute or two with the microphone debacle. How can we test this hypothesis of the cosmic imperative if we can't think our way to a solution? How can we test it? Well, of course, we look for a second sample of life. Where do we do that? SETI is one, but that's maybe a long wait. Planetary atmospheres is another, extrasolar planets. Quite a wait for that one, I think. Synthetic biology, you will hear from Steve Bennett and his colleague later today about the possibility of, as it were, making life in the lab. That may give us an indication of how easy or hard it is, at least for us, to make it. I don't know about Mother Nature. And the one, of course, we all want to talk about is going to Mars. And I'm grateful to Carol for having taken care of the description of Viking, the first and last biological experiment NASA ever did on the surface of Mars, despite what you will read in the press. I also want to pay tribute to Gil Levin. I knew him well. Right up until the end, he was staunchly defending his putative discovery of life on Mars. Time may prove him right. It may be that he really did. The problem about Mars, though, as an abode for life, is that, and it's a term very familiar to us in the age of COVID, it's not quarantined. Earth and Mars are not quarantined from each other. The planets take a hit from time to time from comets and asteroids, and splatters rocks all around the solar system. Earth rocks go to Mars, Mars rocks come to Earth. Is one in our meteorite collection at Arizona State University. We've got quite a lot of them. And so this cross-contamination of the planets by rocks, they trade rocks. They can also trade microbes. It's very clear that cocooned inside displaced rocks, microbial life could travel from Earth to Mars and Mars to Earth. So if we do go and find life on Mars, chances are it's borrowing old Earth life. It won't be the second Genesis that we really need to know. There are all sorts of hazards of interplanetary transfer. I don't have time to talk about why they're not a showstopper. I just want to finish with a pet idea of mine. What's the most Earth-like planet we know? It is, of course, Earth itself. And if life really does get going quickly under Earth-like conditions, as many astrobiologists now favor, as I explained, they didn't when I was a student, now they do, then surely it would have happened many times over right here on our home planet. How do we know it didn't? Has anybody actually looked? And remarkably enough, there's been almost no attention to looking for a second sample of life on Earth, sometimes called a shadow biosphere. There could be aliens right under our noses. There could be an alternative form of life with radically different biochemistry. We would overlook it. Our methods in microbiology are customized to life as we know it. They would not spot life as we don't know it, even if it was right under our noses or even in our noses. So my conclusion is that if there is a shadow biosphere of alternative life, then it will be widespread in the universe. Life will be fundamental. There'll be a cosmic imperative. It won't just be a trivial local aberration. And we won't be freaks, but we'll be the product of an intrinsic, bio-friendly universe. We could feel at home in the universe. And if you find these heartwarming sentiments congenial, then do check out a couple of my books. The Demon in the Machine deals specifically with what is life and how did it arise. And just this month, the new book, What's Eating the Universe and Other Cosmic Mysteries. You will find discussion of many of these topics. And I think I've used up my time, so I'm happy to take questions.
Thank you very much, Paul, for this extremely amazing and fascinating presentation. I especially love the quote about biosphere being the original World Wide Web. That sounds very exciting. So we'll take a couple of questions. We have a few minutes, and I invite everybody to drop their questions into the Q&A. But for now, we have a question from Adil, and they ask, do you know about Dr. John Archibald's concept of a participatory universe? And if so, what is your interpretation of it?
John Wheeler, yes, John Archibald Wheeler was a very great friend of mine, and I would like to think a mentor. He had a great influence on my own thinking. And Bob was kind enough to mention my earlier book, The Goldilocks Enigma, Why is the Universe Just Right for Life? And I dedicated that book to John Wheeler, and I discuss his notions of observer participation. I really try in that book to take the germ of his ideas, which he developed over several decades, and carry them forward, because he didn't really manage to develop them very far. And so I'm quite sympathetic to the idea that the underlying laws of physics and the emergence of life, but more than that, the emergence of mind and this is the key point, comprehension, are written into the structure of the universe. So that this is, if we want to talk about the origin of things, they're all coupled up together. The origin of the universe, the origin of the laws, the origin of life, the origin of comprehending beings, I think are part of what Wheeler felt should be some sort of self-explanatory loop, some self-contained interlocking set of concepts. And I've tried to carry that forward as much as I can in that book. So perhaps I can refer you to there.
Thank you. And the next question is from Ayat, and they ask, what is the best way we can achieve an interplanetary rock travel?
Interplanetary rock travel?
Rock, exactly. I guess that would be a rock, like as a carrier of life.
Yes, so I mentioned that this occurs naturally between planets. Sometimes people use the word panspermia. It's important to realize that the original panspermia had the microbes sort of wafting naked in the interstellar space. It's a very unpleasant experience, but cocooned inside a rock. It's a more congenial environment, but of course the cross-section is much lower. So going from Earth to Mars, Mars to Earth, it's inevitable. Less so from Earth, say, to Enceladus, but not impossible. Going between planetary systems by natural processes is very hard. But could we launch rocks? Could we put Earth organisms into something like rocks and eventually get them hurled out of the solar system and seed life on other planets? Certainly there's been speculation like this. Some people would think we shouldn't be doing that on ethical grounds. Francis Crick, who thought life was so hard to get going, even speculated that it might have been deliberately seeded here in something like a rock sent from a very distant planet. Lots of science fiction written on these things, but in terms of the numbers, they're not very favorable.
Thank you very much for the answers.